Hello, Mr. Betts here. We're going to take a look at how we can use implicit differentiation to take the derivatives of one last category of functions, and that's going to be exponential functions without the base e, so base other than e, some other constant, and logarithmic functions where the base is not e, so log of some other number like, say, like base 10. So I'm going to start with a more concrete example, and then I'm going to generalize it using a variable where the 2 is here. So the idea here is if we want to take the derivative of something like this, we can start by rewriting the equation as y equals 2 to the x. So this would be equivalent to trying to find dy dx then. And what I'm going to do is I'm going to manipulate this equation a little bit first, and then I'm going to take the derivative. So I'm going to take the natural log of both sides, and I want to introduce logs because I want to take care of the exponent here, and there's a log rule that's going to allow me to do that. So I'm going to take the natural log on the left side and get natural log of y, natural log on the right side, and we get natural log of 2 to the x. Now, by doing that, what we can do is we can take this x and we can move it out front. So this is the same thing as saying the natural log of y equals x times the natural log of 2. I didn't arrange my work here very well, so let's move over here. So now both sides of this equation are things that I can take the derivative of using things that we know so far. So on the left side, I want to take the derivative of the natural log of y. And remember, we're taking the derivative with respect to x. So I'm going to take the derivative of the natural log of y, and we get 1 over y. But then that y is a baby function. It's an inner function. We have to multiply by the derivative of that. So we're going to multiply by dy dx. On the right side, when we take the derivative of x times the natural log of 2, this is actually simpler than it looks. The natural log of 2 is actually just a constant. It's just some number. I don't know what the number is. It doesn't matter what the number is. It's just a number. So taking the derivative here is like taking the derivative of something like 7x, which is just going to be 7. In this case, the derivative of that is going to be the natural log of 2. Now we're looking for dy dx, so I'm going to solve for dy dx, and we get y times the natural log of 2. It's the derivative. We've solved for dy dx. We have an answer. However, we were trying to take the derivative with respect to x, so we should expect an answer in terms of x. So all I'm going to do here is make a substitution and get rid of the y. And we defined y at the very beginning as 2 to the x. So y is equal to 2 to the x. So I'm going to replace this y here, and we get dy dx is equal to 2 to the x times the natural log of 2. So implicit differentiation gives us a path to take the derivative of this equation or this expression, even though we didn't know how to do that before. So if we want to generalize that, I'm going to do the same thing here. So I'm going to say y equals a to the x, take the natural log of both sides, and I'm going to jump right to this step here, move that x out front. Then using implicit differentiation, we take the derivative of both sides, multiply by y, and replace the y. So y is a to the x, so we're going to have a to the x times the natural log of a. So this method right here, by generalizing it, we can say that the derivative of any exponential function, regardless of what the base is going to be given by this expression. I'm sorry, that shouldn't be natural log of x. That should be the natural log of a. And keep in mind that if we were taking the derivative of something like, say, a to the x squared, we would have to use the chain rule, so that x squared would be an inner function that we would have to account for, and you could do that with a later exercise. I also want to look at log functions, but logs with bases other than e. So if we want to take the derivative of this, I'm going to use another rule for logs that will be useful to us. So we have y equals log base 10 of x. So there's a rule for logs that's called the change of base rule that says that if we have a log of any base and we want to write that log in terms of another base, in this case, I want to use natural logs because we know how to take derivatives with natural logs. So a log of any base of some number is going to be the log of any base that we want. So I'm going to introduce C here of A over the log of that same base of B. So what I can do here is I can choose this new base to be E, and we have natural log of A over the natural log of B. That helps us here because then we get the natural log of X over the natural log of 10. Okay, now we don't even really need to use implicit differentiation. We just take the derivative of both sides. So we have dy dx is equal to, I'm going to think of this as 1 over the natural log of 10 times the natural log of x. Remember, this is just a constant right here. Constant multiple rule says we just carry that along. So 1 over the natural log of 10. And then the derivative of natural log of x is 1 over x. So simplifying here, we're going to have 1 over x times the natural log of 10. So I'm going to generalize again with this. So we say y equals log base of any base we want of x. And so we rewrite that as natural log of x over the natural log of b. So taking the derivative then, we have dy dx equals, so the derivative of natural log is 1 over x, and then that natural log of b as a constant just stays as it is, and this gives us a formula for the derivative of any natural log of any, or I'm sorry, any log of any base. So these are two formulas that you might want to memorize. You might not want to go through that process every time you want to take the derivative of something like this. I do want to point out that if we put an e in where the a is here, we get e to the x times the natural log of e. The natural log of e is 1. So this formula works even if that base is e, because we get the derivative of e to the x is e to the x. Same thing here, if we have log base e, then we end up with 1 over x times the natural log of e, and the natural log of e is 1, so it's just 1 over x. So that the derivative of the natural log is 1 over x using this formula also.